Hello and welcome back. If you are new here, please subscribe to the channel, give this video like, and click the bell button to get notification when we upload new video. Thank you. Today's video will be a full tutorial for infrared LED diode QED234. Unlike common, white, red, blue, green and yellow LED diodes, that we are all accustomed to, infrared LED diode emits light in the wavelength of 850 and 940 nanometers. This light is invisible to human eyesight. You can see implementation of this type of LEDs in all sorts of TV remotes, elevator doors, other types of doors that open automatically, and etc. This, and following video, are prerequisites for the video we plan to make, where we will implement infrared LED diode and infrared receiver, together with NPN2N3904 transistor, to make detector circuit. The QED234 is a 940 nanometers gallium arsenide or aluminum gallium arsenide infrared LED encapsulated in a clear untinted, plastic T1/3/4 package. On the screen, from left to right, we can see rendering of the diode from the manufacturer, real-life photo, and at most right, is the electrical symbol how the diode is represented in the electrical circuits. The QED234 is an infrared LED that emits light at a wavelength of 940 nanometers, which is commonly used in remote control and sensing applications. It is built using a gallium arsenide chip with an aluminum gallium arsenide window, allowing for efficient infrared output. The LED comes in a standard 5mm clear plastic package and produces a focused beam with a medium emission angle of about 40 degrees, making it suitable for directional transmission. It delivers high output power and is designed to work well with matching photosensors such as the QSD123 and QSD124. Thanks to its clear, untinted housing and reliable performance, the QED234 is widely used in infrared remote control systems. It is also a LED-free device, compliant with modern environmental standards. Before we move on to the absolute maximum ratings, it is important to keep in mind that many manufacturers obtain parameters for their components under highly idealized test conditions. Instead of using a continuous DC current, they often apply short bursts of pulsed signals with very narrow pulse widths and long intervals between pulses. This approach minimizes self-heating and can result in parameter values that are significantly higher than what can be achieved under continuous, real-world operating conditions. Such test conditions are rarely encountered in practical applications of these components. Now that this is out of the way, let's move on to the absolute maximum ratings section of the datasheet. As the name suggests, these ratings define the maximum values of various parameters that the component can withstand under laboratory test conditions. In real-world applications, a common rule of thumb is to operate well below these limits, often around half of the specified maximum, to reduce thermal stress and extend the component's lifespan. This guideline is particularly important for voltage and current ratings. First two parameters define operating and storage temperature conditions. The operating temperature specified in datasheet refers to the range of ambient temperature, surrounding air or environment, in which the electrical component operates. This is not the internal temperature of the component itself. The storage temperature of an electrical component is defined as the specified range of ambient temperatures, minimum to maximum, within which an unpowered device can be safely kept without causing permanent degradation, functional failure, or significant reduction in its future operating lifespan. This range refers to the environmental temperature surrounding the component while it is in storage, waiting to be assembled, or in a power-down state. The next two parameters specify the allowable soldering temperatures for manual soldering with a soldering iron and for automated soldering using machines or robotic systems. The first parameter indicates that the component can withstand exposure to a soldering iron at 240 degrees Celsius for up to 5 seconds without sustaining damage. In practical terms, this means that when the soldering iron is set to 240 degrees Celsius, the soldering operation must be completed within that time limit. The second parameter defines the maximum temperature and duration the component can tolerate during automated soldering processes. For both soldering methods, the following recommendations apply. RMA flux is recommended, methanol or isopropyl alcohol may be used for cleaning, and the soldering iron tip should be kept at least 1.6 mm away from the plastic housing of the diode to prevent thermal damage. The next parameter indicates that the diode can withstand a continuous forward current of 100 mA. Let's put together a simple circuit to demonstrate this. The circuit uses a 5-volt power supply, a 34-ohm current-limiting resistor, and an average LED forward voltage drop of about 1.6 volts. Under these conditions, the resulting current through the circuit is approximately 100 mA. However, if this circuit were powered by a continuous DC supply and allowed to operate for an extended period, the LED would overheat and eventually fail. It is important to remember that this current rating is specified under pulsed operating conditions. In other words, the diode can tolerate a forward current of 100 mA only when it is driven by a pulsed signal rather than a continuous DC source. To be on the safe side, rule of thumb is to use half of the maximum power rating for continuous forward current. If the diode is accidentally connected in reverse in the circuit, the reverse voltage rating tells us the maximum voltage it can safely handle without being damaged. For this diode, that value is 5 volts DC. Applying a higher voltage in reverse could cause the diode to fail, so it's important to respect this limit when designing or testing circuits. Let's remind ourselves that power is calculated as the product of the voltage drop across a component and the current flowing through it. For this LED, the maximum power it can safely dissipate is 200 mW at an ambient temperature of 25 degrees Celsius. For example, if we use a 5-volt DC power supply, the maximum current we can safely run through the diode is 40 mA. As noted earlier, this maximum power rating is obtained under controlled laboratory conditions using a pulsed DC signal. For continuous DC operation, it is recommended to use roughly half of this value to avoid overheating. Additionally, the power dissipation decreases linearly by 2.67 mW for every 1 degree Celsius increase in ambient temperature, when ambient temperature is above 25 degrees Celsius. LED peak forward current is the maximum allowable instantaneous current for DC short pulses, in our case 100 microseconds, with 1% duty cycle. It exceeds the continuous forward current for high-intensity, pulsed operation, but exceeding this rating risks rapid burnout. So, if we would apply DC pulse power source that could provide 1.5 amperes of current, our LED would be able to withstand this current for a very brief period of time, before burning out. Under no circumstances should you operate LED under these conditions when using continuous DC power source. Next item on the list are electrical and optical characteristics for infrared diode. As before, in small print, the manufacturer informs us that displayed values and characteristics are obtained under very specialized laboratory test conditions. Such test conditions are rarely encountered in practical applications of these components. The first parameter is the peak emission wavelength, marked by the Greek letter lambda. This specification tells us that under test conditions, with a forward current of 20 mA, the dominant wavelength of the light emitted by the diode is 940 nanometers. This places it near the far end of the infrared spectrum. It's also worth noting that infrared LEDs are available with different peak wavelengths, such as 850 nanometers, depending on the application. No LED emits just one wavelength of light, instead, they emit narrow spectrum of adjacent wavelengths, depending on the purpose and quality of diode. This parameter tells us that of all those wavelengths emitted in the spectrum, the one with wavelength of 940 nanometers is the predominant and most powerful one. Next parameter, the spectral bandwidth, closely relates to previous one. It tells us that under test conditions, with a forward current of 20 milliamperes, the width of spectrum of broadcasted wavelengths is minimum 50 nanometers, but it can be more. Assuming that distribution to the right and left from the peak wavelength is uniform, the diode emits light with wavelengths ranging from 915 to 965 nanometers. Next parameter tells us that under test conditions, as the temperature of diode increases, the peak emission wavelength shifts toward longer wavelengths, lower energy. This is known as a positive temperature coefficient of wavelength. This means, as our diode heats up, with increase of diode temperature by 1 Kelvin, the peak wavelength shifts by 0.2 nanometers. For example, if our diode heats up by 60 kelvins, from test ambient temperature of 25 degrees Celsius, the peak wavelength of the diode will shift from 940 to 952 nanometers. It will redshift to lower energy wavelengths. In relative terms, 1 degree Kelvin is equal to 1 degree Celsius, but the scale starts from different point. This parameter describes how far the light spreads to the left and right of the diode's central axis. The typical value is 40 degrees, which means the diode emits light approximately 20 degrees to each side of the centerline. Forward voltage parameter tells us that under test conditions of forward current of 20 milliamperes, and pulse DC power source, where pulse period is 20 milliseconds, and pulse width is 100 microseconds, the voltage drop across diode in the circuit is maximum 1.6 volts. Have in mind that amplitude of the DC power source signal is not specified. Now, this parameter really tells us nothing. It is more likely than not, that in real-world scenario, we will use continuous DC current source, with discrete voltage of 3, 5, 12 or more volts. Unfortunately, to determine real voltage drop for circuit of our own design, we will have to manually measure voltage drop across the diode and do the calculations for resistors and current ourselves. Temperature coefficient tells us how voltage drop across diode changes with change in temperature. For test conditions, increase of 1 Kelvin of ambient temperature causes 1.5 millivolts of voltage drop across the diode. For example, if ambient temperature rises from 25 degrees Celsius, by 20 kelvins, the voltage drop of diode would go from 1.6 to 1.57 volts, it would decrease by 30 millivolts. Please have in mind that in relative terms 1 degree Kelvin is equal to 1 degree Celsius, but starting points differ. Next, if we were to connect our diode the wrong way, flip it, and connect anode to negative, and cathode to positive DC power source of 5 volts, reverse current through the diode would be 10 microamperes. This is well-known diode reverse current. Also, please have in mind that datasheet has an error, it should write microamperes, not nanoseconds. Way to go, manufacturer! Again, we have an error in datasheet. Radiant intensity is measured in milliwatts per steradian, not in nanoseconds. It represents the concentration of infrared light, often indicating how bright the IR source is in its peak emission direction. High radiant intensity is crucial for long-range or high-sensitivity, proximity sensing. Next, again the same error, the measurement unit should say percentage per 1 Kelvin degree. This parameter tells us that by increase of 1 degree Kelvin, forward current drops by 0.3%. So, under test conditions, a forward current of 20 milliamperes, if temperature rises by 20 degrees, the forward current would drop by 6%, from 20 milliamperes to 18.8 milliamperes. And at last two parameters tells us that under test conditions of forward current of 100 milliamperes, it takes 1000 nanoseconds for the diode to switch off or on. Pretty simple, but please have in mind that this parameter is obtained under test condition of pulse DC power source and forward current of 100 milliamperes. These are not real-life scenario conditions. It is really shame that this particular manufacturer opted to publish datasheet with so many errors. Let's correct these mistakes and display proper datasheet for electrical and optical characteristics for infrared LED. Now, that good deed has been done, let's take a quick look at some graphs that manufacturer provided and give a quick explanation. Let's hope that there are no more errors in the datasheet. Unfortunately, again, the manufacturer opted to present us with parametric graphs obtained under totally unrealistic laboratory test scenarios. Figure 1 and 2, both shows us parameters obtained under pulsed DC power source, of unknown amplitude, with pulse width of 100 microamperes, and period of 10 milliseconds. Figure 1 shows us how diode intensity changes with change in forward current. Have in mind that graph is presented in logarithmic scale. Figure 2 shows us how voltage drop across diode falls with increase in ambient temperature. Again, nothing of this is applicable to real-life scenarios, where we use continuous DC power source of certain voltage. We will skip figures 3 and 4, as they really tell us nothing of importance for our needs. Figure 5 tells us how voltage drop across diode increases with increase in forward current. Please, have in mind that vertical axis of the graph is presented in logarithmic scale. This is the only graph, out of 5 in total presented in the datasheet, where we can read some valuable info for our circuit design. For example, if we want to run current of 20 milliamperes, we can read from parametric graph that expected voltage drop across diode would be around 1.2 to 1.3 volts. This was fun. We have learned everything we needed on how to read datasheet for infrared LED and understand the parameters. These same principles apply to most of LEDs, infrared or otherwise, as the parameters are very similar. We even corrected the errors in datasheet ourselves. In next video we will go over infrared receiver. They are usually paired with infrared diodes to make detection circuit. You might be surprised to learn that infrared receivers are very similar to NPN transistors themselves. So, please stay tuned for our next video. And before you go, it would mean so much to us if you would give this video a like, post a comment, or question in comments section, and please subscribe to our channel. See you soon. Bye.